Okay, in this physics video we're going to talk about temperature. And so temperature essentially is just a measure of how hot or cold something is. And we'll talk more about thermodynamics and heat energy and things like that a little later on. But for now, we're just going to focus on measuring the hotness or coldness of something by measuring its temperature. Another thing to keep in mind here is the effect that temperature has on physical materials. Most materials expand when heated. So in the last video we talked about all the little atoms that make up solid materials or any kind of material, and when it's in a solid state, those atoms are regularly arranged and they hold their form, and in the extreme case, when it's turned into a gas, they're very far apart, they're irregularly spaced, and they're moving all around, lots of movement, and they're colliding with each other, bouncing off each other. So if you kind of think of this as a spectrum, from being very, very rigid, very unmoving, very organized, to spaced very far apart, irregularly moving all around, you can kind of imagine how, as you increase the temperature, these molecules begin to move around a little bit more and get a little bit further apart, which is why most materials expand when their temperature goes up, when they are heated. So thermometers have been around for a really long time. Thermometers are just instruments used to measure temperature. I have one of these types of thermometers in my home. This is a Galileo thermometer, and the way it works is you have all these glass bulbs inside of it. They're sealed off, they're closed, and they contain air and a colorful liquid. And each of them are connected to or each of them has a metal tag connected to it, which has a temperature written on it. So the thermometer works on the principle of buoyancy. When the fluid inside, which is usually just water, when its temperature goes down, let's say, temperature goes down, the molecules get closer together, and the fluid becomes more dense. The denser fluid will cause more of these bubbles to float, these glass bubbles, and so they rise to the top. If the temperature goes up, the molecules get farther apart, and so therefore the fluid is less dense, and in the less dense fluid, these glass bubbles will drop. And so the way you read the thermometer is looking at the lowest glass bubble that is still floating. So it has to be, when it's made, it's calibrated in such a way that the weights of these various bubbles will sink or float at the corresponding temperature that can be read on this metal tag here. So as the temperature goes up and down, the density of the fluid changes, and the glass bubbles either sink or float. So, pretty creative way of measuring temperature. Some other examples of thermometers, probably the most common one that you are used to seeing is a tube, a closed tube with a fluid inside it and a reservoir at the bottom. The fluid used in these types of thermometers used to be mercury. Today it's more likely colored alcohol, and again, as the temperature increases, the fluid expands, and as the fluid expands, it rises up the tube, and the tube is calibrated with marks along the side to measure the temperature. As it gets colder, the molecules get closer together, it becomes more dense, the fluid contracts and lowers, and again you just read the marking along the side of the tube. Thermostats, and in this case it looks like an old oven thermometer, can be made with what's called a bimetallic strip. So the spring you're seeing here in the middle, coiled up, is actually made of two different types of metals, shown here in the diagram, one green, one blue. And when they are heated, the two metals will expand and contract at different rates. In this case, it's being heated. The green one is expanding more than the blue one. So rather than expanding in a straight line, it curves off to the side because the green one is expanding more than the blue one is. And so that when that type of strip is wound around in a circle like a spring, it will move the indicator here in a circular motion. And so again, it's calibrated with the markings on the dial so that you can read the temperature based on how much that spring winds itself up or down. So of course, in the United States, we do not use the metric system typically. And sometimes I think that is rather unfortunate because the metric system does make a lot more sense if you really think about it. And I'm not going to play it here in this recording because the audio wouldn't pick up. But I'll try to remember to post this as a separate video, or it will be included in the PowerPoint on Blackboard if you it's embedded in that PowerPoint if you download it and go through the PowerPoint on your own. I have an audio file from I think it's from a British comedy radio show, and it's a funny little sketch. What happened if Celsius and Fahrenheit, if those two gentlemen happened to meet each other and have a conversation? So those are the two scientists that came up with the two different temperature grades that we use. We use Fahrenheit here in the U.S., and it's kind of a strange, setup, really, when you think about it. Freezing is 32. Why 32? It's complicated. And then boiling is 212. Again, why 212? I don't know. That seems pretty strange as well. But the Celsius measuring system, the units of Celsius, make a lot more sense. Freezing of water is 0. That makes sense. And boiling of water is 100. So it just makes more sense. Why don't we use it here? Well, we're just not used to it. We're used to Fahrenheit, and we just don't like to change. So that's that. But in physics class, in scientific problems, the scientific community does use the metric system. So we'll have to get used to using degrees Celsius, at least for our physics problems. So let's just do a quick unit conversion problem here. Normal body temperature is 98.6 degrees Fahrenheit. What would that be on the Celsius scale? What's the average human body temperature on the Celsius scale? Well, the process you have to go through is kind of think, how many degrees above freezing is it? So on the Fahrenheit scale, we're at 98.6. So if we take 98.6 degrees Fahrenheit and we subtract from it 32 degrees Fahrenheit, which is the freezing point of water, we get 66.6 degrees Fahrenheit. So that's how much we are above freezing. Okay, and so the scale on Celsius, the number of degrees between freezing and boiling is 100. The number of degrees on the Fahrenheit scale between boiling and freezing is 212 minus 32, which equals 180. And so if we look at that ratio of degrees Celsius to degrees Fahrenheit, going between freezing and boiling, it takes 100 degrees Celsius for every 180 degrees Fahrenheit. Now, this ratio or conversion factor can be simplified. 100 over 180 is equal to 5/9. So we can take our degrees Fahrenheit, subtract 32, and then multiply it by this ratio of 5/9. So 66.6 degrees Fahrenheit multiplied by 5/9, and we get 37.0 degrees Celsius. So if you were concerned if you had a fever and you measured your temperature with a Celsius thermometer and found that your temperature was 37 degrees, then congratulations, you have normal human body temperature. We're going to move on now to what I think is sort of a funny named law of thermodynamics, and that is the Zeroth Law of Thermodynamics. Now, why on earth would anything be named Zeroth? Well, essentially what happened was they developed a first law of thermodynamics, a second law of thermodynamics, and then they realized, oh, wait a minute, there's really this law of thermodynamics that is more fundamental, that really needs to come first. But since we've already come up with the first law of thermodynamics, what are we going to call this one? How can we name this so that it comes before the first one? And that's how they came up with the Zeroth Law of Thermodynamics. So thermodynamics basically is, if we look at the root word, it's the way that heat flows. Thermo being heat and dynamics is motion. So how does heat move from one area to another or one object to another? And the Zeroth Law of thermodynamics says if two objects are in equilibrium, meaning the same, with a third object, then they are also in equilibrium with each other. So this is kind of like in algebra what we're saying, like if A equals B and B equals C, then A equals C. That's called the transitive property of equality in mathematics. And so for us in thermodynamics, that's basically the Zeroth Law of Thermodynamics. If two objects are each equal to a third, so we're saying if B is equal to A and B is equal to C, then C is equal to A, or A is equal to C.